Okay, we're going to go over linked lists and hash tables from that we just didn't have time to cover in class. So I'm going to do it in CLion just because it's easier. But of course, it doesn't matter what IDE you use it in. Whenever I start a project in CLion, I always just like to run the hello world just to make sure everything's working okay. And there we go, hello world, cool. All right, so let's do a linked list. So we need to make a structure to hold our linked list. Call it list S. And again, this is classic linked lists. If you remember from your 46A or B that you did linked lists in. So we have a next pointer and we have data. So we'll store a character, a string. Now, we're only going to do a singly linked list, so we don't have to worry about previous pointers or back pointers. And so for the head will just be a pointer to the first element. So we don't really need an extra structure for that. So let's just say struct head is going to start out as null because it's empty, right? A null indicates an empty list. And the way we go through a list is we say, we'll start up a pointer, or we'll get a pointer. So let's do a for loop. Struct list star, pointer equals head. We're going to start it at the head. And well, it's not null. Then we'll continue. And then the condition we loop on, or the change we need to make every iteration is just to move to the next one. So this will be our basic loop. Now head, I did not put the structure type in here. And I will print the string for the given pointer. So let's put that in here. So now this is an empty list, so nothing should happen. Let's see that nothing happens. Oh, nothing happens. And here we see that even the compiler knows that nothing's going to happen, right? Because the head is null. So let's make it so that we can add to the list. So let's have an add function. We can say void add to list. Now we're going to pass in the head. Struct. And we're going to pass in the string that we want to add. Now, what we're going to do, we can add to the end, we can add it in order. The easiest thing to do with a linked list is to add to the beginning. You can actually do it in 2 lines of code. So think about for a second, can you do this in 2 lines of code? What should those 2 lines of code look like? Because we're just adding it to the beginning. So take a moment to think about that. Let's do that here. Actually, I think it might be 3 lines of code. I might have lied, but let's see. So we're going to need to allocate a new node. So let's allocate that here because this is going to be a new linked list node. So we'll call it new node. And we're going to allocate, we're going to use malloc, and we're going to do size of new node. Now, when you do this size, doesn't like, actually I can be fancy and let the IDE do it by just doing Alt-Enter. Oh, it imported malloc. I think the right thing to do is stdlib. So let's do the right thing there. Um, one pitfall here is that instead of doing size of the dereferenced new node, which would be the size of list S, if you just do this, it'll be 8 bytes because you're doing the size of a pointer, and we want to allocate enough space to hold a node. So that's why we need to dereference it. Okay, so we are going to set new node str to be the character we're keeping, the string we're adding, and new node next to be the head, right? Because we're appending on the head. Now we need to change the head. Now you notice, okay, you notice a couple of things. We're going to use 4 lines and not 2. I was overly optimistic there. But if we do this, next, this isn't going to work. Oh, sorry, new node, not next node, new node. This isn't going to work. It compiles okay and everything, but head is head. If we just change head, that value goes away when this function returns. What we really want to change is the original head. So when we call this, if we pass, let's say we do add to list. Let's say node 1. Okay, and then let's add this a couple of times. Let's do 3 of them. Now, we really want head to change, but the way we're passing head in here, it's not going to change. Head is a pointer, and we're passing the we're passing a null in this first case, and we're not going to change head. It'll still be null after the call. We actually want to change head itself. So we want to change the address where that null is stored so that the add to list can change that null to the new node. Now when we do that, we need to say now that head is going to be a pointer to a list node. Okay, of course that's going to change here because next we want to point to what head was originally pointing to, and now we want to change the bytes that store the head pointer. We want to change those to point to new node. So this should do what we want. The compiler seems happy. Let's run it and see what happens. Okay, here we go. We see that we printed those 3 nodes. We see that we printed them backwards. That's because we're basically implementing a stack here. We always add the new one onto the front of the list. So when we print the list in order, we're going to get the last in first. So this looks kind of cool. So what we can do, we'd like to time it. So let's go. Wait, actually, before we do that, there is something to note here. There's a question of ownership. This new node, or this node 1, this string, there's a pointer to memory that we're passing as str, as that second parameter. That pointer points to a region of memory that stores a string. Now there's a question of ownership and lifetime. Who owns that string? And who's in charge of cleaning it up or freeing it? Now this string that we're passing in, it never changes. Like these are constants, right? They're called literals. So we don't really have to worry. But what if we change it? So what if instead of doing it that way, we do something like this, buffer, call it 1024, and then we do str, we'll copy node 1 into the buffer. You can do Alt Enter to import the right thing. Oh, we can't find it. I think that's in, if I remember correctly, it's in string.h. Did it work? Yes. Okay. And then we can pass buffer here. So this is kind of, this matches a little bit more what your program often does. Actually, let's match even. Oh, okay. Well, yeah, this matches pretty closely what your program does. So instead of stir copy, you're doing a scanf. So but we keep doing this buffer. So we keep copying a string into a buffer, and then we print the buffer. Now, the thing that's interesting is to think about what this is going to look like when it's done. You see that we got node 3 over and over again. Now, why? Why did we get node 3 over and over again? Well, when we added to the list, we were adding a pointer to the location where the string was stored. That's what we put into the list. Not this. It's not really the string itself. It's the pointer to where the string is stored. And the pointer to where the string is stored is always buffer for all 3 nodes. And we keep changing what's stored in buffer until finally we have node 3 in there. So all 3 nodes are pointing to the same memory location. And the last thing that was stored in that memory location was node 3. So when we print out the list, we get node 3. So, how can we fix this? There's a couple of ways to fix it. We can, in here, we can do a stir dupe. So a stir dupe is just malloc str +1 followed by a stir copy of the address we get from malloc and the string. So that's what that is shorthand for. That's what that function does effectively. So if we do this, then we're actually storing a copy of the string. So each time we get a different address. So if we print, actually let's use the debugger just to see. Actually let's use the debugger before and after. So let's leave this what it was before. So when we run the debugger here, we see that buffer, okay, well, let's step into it. So actually, buffer, if we look at the address, so can we see the address of buffer? Not very nicely. Why? Oh, wow. So if we go to GDB, we can say print buffer. Well, that's going to print the value. Examine buffer. So this is the address of buffer right here. This 7F and then it ends in 9F0. So and actually, I don't know, is the memory view interesting? Maybe not. Okay, so anyway, here's buffer. Yeah, now I'm just so curious to see what else we can see in the debugger. Anyway, okay, so let's go step into our stir copy. Oh no, we're not going to step into the stir copy. We'll step over that, and then we'll step into our add to list. So if we look at add to list, there is the address of buffer. Do you see how it ends in that 9F0 and it contains node 1? Okay, we'll step through that. Bonk, 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 bonk. And if we look at new node, Now it's that string pointer is pointing to the address 9F00, and the debugger is helpfully showing us that node 1 is stored at that location. So we step through, and then we do another string copy. And now when we do add list again, we step in and we look, and again, str is 9F00. We step over. Now new node str is that. So basically everything's pointing to the same location. So let's change. Let's put the stir loop in and run it again. Okay, so now we'll step over. We'll step into the add list. Now you'll notice str is E300, right? That's what buffer is. We step in over it. Now, when we look at new node, the address of str is different from the address of the string that was put in because we copied it. We allocated new memory to hold a copy, and we copied it. So now when it changes, it's going to change. When we change buffer, it's going to change a different memory location, and we're going to keep copying the string. So if we then run this, we'll see, we look at the console, we see that it prints correctly. So this is what we want to happen here. And now the way we've done this list, we know that add to list makes a copy of the string. So this str that's in the list is owned by the list. It has its own copy. So that's important if we need to free, because right, the list, since the list made a copy, the list needs to make sure it gets freed.